Hi all, welcome to a new video. Today we are going to discuss about the deletion of actually we are continuing the deletion of a binary search tree. Last class we discussed about the binary search tree deletion, and we completed the first case of binary search tree deletion of a leaf node, and the remaining three cases are deletion of a node with one child and deletion of a node with two children. These are the cases that we have. We completed the first case of deletion of a leaf node, and second case deletion of a node with one child that we are going to discuss today. And how will we identify? So last videos we discussed about what's P and how we reach to the exact location of that particular node that we are going to delete. So T represents a particular node and node for deletion, and P is a variable that represents the parent node, always represents the parent node's address, because it's considered as a tracing variable that we discussed in the last video. Please refer the last video for clarification. And P contains its previous node, that means this parent node's address, and T is a variable contains the node's address, and that node is going to get deleted. And in this case, T is a node and T tends to write equal to null. So T tends to write equal to null in the sense T's left address field is available, but T's the node's right address field is empty. That means right element is not available, that is having only one left child. So this is a case. If T tends to write equal to null, then what we are going to do? We are going to delete that particular node and make the updations on its parent node. For example, in this case, in this tree, we have element 25 with one left child, and the right address field is null. So the process that we are going to do is, we identified the element where we located 25, where and that address is available with the variable T, and its parent node's address is available with the variable P. So P is a variable contains 100 and T is a variable contains 200, and 200 is the address of 25, and that element is we are going to delete. In this case, the step is once after the deletion in the sense the process of deletion is like this. If you want to delete 25, what we are going to do is this parent node's left address field has to be reassigned as the node's left address field. 300 has to be reassigned on 35's left address field. That is the process that we have to do. So we make the changes on its parent node's left address field. That is the process. So first step is to confirm that the element that we are going to delete is a root node or an internal node. Two possibilities are there. It may be a root node or it may be an internal node. For example, in this case, this is one of the cases that 35 is element, consider 35 is element that we are going to delete, and 35 is a root node, and as well as the node having only one left child. Right address field is null. So this is another possibility. So first step is to identify whether the element that we identified for deletion is a root node. So how will we identify? We can simply write like this: if root equal to P, sorry, T is the element that we identified for deletion. If root equal to T, then what we have to do? We have to reassign the root address. So here already root represents address 100. Now we are going to change the root address as 200. So 200 is available with the element's left address field, because right address field is null. That is why we reached here. So we can directly say that root equal to T tends to left. Very simple. So we completed the process if it is a root node. So if this is not a root node, else. If this is not a root node, else if. What's the next step? For example, in this case, consider 25 is the element that we are going to delete, and T contains address 200, P contains address 100. So what we have to do? We have to make the updation on its parent node. So our task is to confirm whether the parent node's left address represents 200 or whether the parent is right. We don't know, because P is a tracing variable. We just know the address of its parent node with the variable P. So next step is to confirm that the parent node's left address field is 200 or parent node's right address field equal to 200, because if we confirm that, then only we can make the updations accordingly. So first step is to verify whether P tends to left equal to T. If this is the case, P tends to left equal to T, then what we have to do? P tends to left equal to, we are reassigning the value of left value in the left address field. T tends to left because right address field is null. Okay, that means P tends to left, that is what, 100 tends to left. P represents the parent node, that is 100. 100 tends to left, which is equal to T tends to left 300. So this will be reassigned as 300 after that statement. Okay, if this condition is false, that means P tends to left not equal to T, then automatically P tends to right. So else we are confirming that P tends to right equal to T. So actually we don't want such kind of a statement because there is no other option for that. So I can directly write a program for that. What is the program? P tends to right equal to T tends to left. Okay, that's all. Very simple. And last step is to make that address free. For that we are using the function free of T. Very simple. So we completed the element to delete a node with having only one left child. Similarly, we can write the program for the opposite case. That means if left equal to null instead of right, if left equal to null in the sense to delete a node having only one right child. If so, we have to make the changes accordingly. T tends to left equal to null, so we have to make the updations according to this. T tends to left will be replaced as T tends to right. Very simple. So this is a way that we are going to delete the element with the one child. Thank you for watching the video. Any doubt, please contact me for a clarification. Thank you.